Okay, so this is the outline for chapter 31. So we'll talk about the LC oscillator without any resistance. So yeah, so it has a simple harmonic motion. And next we'll talk about the damped oscillation, which means that the LC oscillator are actually in series with a resistance, or it has some intrinsic resistance inside, so that the sine wave will attenuate. So the energy will be consumed by the resistor. And then we'll talk about the forced oscillation, which means that if we input the sine wave to the RLC circuit, what will it be, and whether we have some tools, mathematical tools, to simplify the calculation. And we will also consider if we have RLC in series, and then we try to input the sinusoidal wave to the RLC circuit, what will it be? And then we talk about the power, which is related to the root mean square I just mentioned. Finally, we'll talk about the transformers. Okay, so here it demonstrates the electromagnetic oscillation. So there are many descriptions. So it's like, simply speaking, we have a circuit like an inductor is in series with a capacitor. We don't have any resistance. We don't consider any resistance. And then initially, we already store some energy. For example, let's choose either one of them, maybe this one. The capacitor is charged, has some initial charge. So if you still remember, you know the energy storing here is like 1/2 CV squared. 1/2 CV squared is the energy stored in the E field within the capacitor. And you can also choose another way. But here, for simplicity, we have all the energy stored in the capacitor and no energy stored in the inductor. Of course, you can still have this one as the initial if you like. So in that, or it should be this one. So you don't have any initial energy stored in the capacitor and all the energy stored in the inductance, which means that we have current going through the inductor, and then no charge accumulate on the capacitor. It's up to you. But let's start from here. Let's start from here, which is the part A. So in that case, all the energy are stored in the capacitor. So we have a UE to be maximized, and then UB is 0 because the energy stored in the inductor is like 1/2 Li squared. 1/2 Li squared. So initially we don't have any current. Okay, so if I just put it like this, and then at the next moment, then the charge will start to discharge. Okay, so it starts to discharge. So the voltage here will decrease. The voltage here will decrease, and there will be some current. So in that sense, I is increasing, and then V is decreasing. So for some moment later, then there will be a moment that the energy stored in the inductor will be the same as the energy stored in the capacitor. UB equals UE, which means that at some of the moment, 1/2 Li prime square is actually 1/2 CV prime square. Okay, for some moment. Of course, in between, UE is larger than UB, and then UE is decreasing because V is decreasing, and then UE is decreasing, and I is increasing, like this. Okay, so up to a point, UB and UE are the same. And this process will further go on until UEE becomes 0, which means that no any charge are stored in the capacitor. All the energy are transferred to the energy stored in the capacitor, which means that current is maximized. In that case, UB is also maximized, and UE equals 0. Okay, so in that case, the current will still keep going. The current will still keep going. And then originally the top plate is plus, has a positive charge, and the bottom plate has negative charge. So for this step, the positive charge will go to the bottom plate, and then the top plate will have a negative charge. Okay, so, but actually it is 1/2 CV squared. So whether it is positive or negative, it doesn't really matter to the energy. So yeah, so we still have a positive UE and positive UB. And then UB in this stage is, UB is decreasing, UB is decreasing, UE is increasing. Okay, so up to a point UB equals UE, and finally UB becomes 0. And then all the charge will go to the bottom, positive charge will go to the bottom plate. So this, for these two, UE are maximized, UB are 0, but yeah, for when you consider this capacitor and this capacitor, yeah, the polarity of the charge are in opposite side. Okay, so this step will move forward, and then UE becomes smaller, and then UB increasing, and then going back, finally back to here. So it's like in simple harmonic motion. The energy stored in the capacitor and the inductor are transferred to each other back and forth. Okay, so here we know UE is 1/2 CV squared, and you also know that Q equals CV. So if you just express this as Q squared, Q and C, which means that you can actually substitute V equals Q over C. Put this 1 to here, then you can eliminate V. It turns out to be Q squared over 2C. Here we have 1/2 Li squared. Okay, so here we talk about the analogy between the block spring system, or to me, I usually like to call it a spring mass system. Spring mass system rather than block spring system. Okay, compared with the LC oscillator, because we only have an inductor and capacitor for the oscillator. Okay, so there will be some analogies. For the spring, it is 1/2 kx squared, and as much as you should know the Hooke's law. Hooke's law is like F equals negative kx. F equals negative kx is the Hooke's law. Okay, so the energy stored in the spring is 1/2 kx squared. So it is correspond to this one. And then for the kinetic energy, so for the mechanical energy, we have potential energy and the kinetic energy. And for the electrical energy, yeah, we can separate the energy to be stored in the capacitor, stored in the E field, or energy stored in the B field. Okay, so which means that if you just change X to be Q, and then you change K to be 1 over C, V to be I, and then M to be L, then you can change all the formula related to the block spring system to the LC oscillator. And you will also get omega to be 1 over LC. So yeah, so it is just some analogy. So we can also see that why we can get those results with a mathematical way. So here we use the energy method. Actually, when I try to teach this course, before I try to teach this course, honestly, I haven't seen this yet. Yeah, it feels like it is the first time I see this energy method, which is quite interesting, honestly. So yeah, let's see what it is. So it tried to consider the total energy stored in the system. which means that the total energy is of course UB plus UE for the LC oscillator, and UB is 1/2 Li square and UE is 1/2 CV square, or here it just write it as Q square over 2C. Okay, so this is the total energy. And as much as we don't have any energy loss, which means we don't have any resistor, so no energy is consumed in any sense, which means that the energy inside the system doesn't change, which means that if we try to take the derivative of the total energy, E with respect to time, it should be 0 because this U doesn't change with respect to the time. Of course, the energy may be transferred from UB to UE and then UE to UB back and forth, but the total energy doesn't change at all. So after we add them together and then take the time derivative, it doesn't change. So let's see how to calculate du dt. So the first term is 1/2 Li squared. So L over 2 is a constant. L over 2 is a constant. So when we consider d 1/2 Li squared dt. Okay, so first 1/2 L is a constant. So it just turns out to be 1/2 L. And then here we have a d dt, and then we have I squared. Okay, so this is I squared. When we take the derivative, it becomes 2I. So it becomes 2I. Okay, so it doesn't end yet because I is a function of time. So we need the chain rule. Chain rule is like we also need to take di dt. So finally, 2 and 2 can be cancelled. So if you only have Li times di dt. And then similarly for this one, when you try to take the derivative 2c, okay, you have 1 over 2c, and then q squared, when you take the derivative, it becomes 2q, and then you also need the chain rule, which is a dq dt. And when we consider dq dt, this is the current. So it turns out to be q over c and then times I, which is q over c or dq dt. Okay, just leave it there. So we just keep dq dt there. But we also know that this I is dq dt. So finally, we can plug in I equals dq dt there. So it becomes a second derivative. So it turns out to be, okay, so here we have, actually this is I. Okay, so as much as we don't expect I to be 0, so we can just divide I on both sides. So it turns out to be L di dt, and then plus q over c to be 0. Okay, we just divide I on both sides. So this I and this I will be cancelled. This dq dt is actually I. So this I and this I also cancel. So we only left with L times di dt plus q over c to be 0. And then finally, we also put in I to be dq dt. So here it becomes L d2q dt2, the second derivative of q, plus q over c equals 0. And then we try to normalize the leading coefficient. So it becomes a second derivative of q with respect to time plus 1 over LC times q equals 0. Okay, so this is actually this one. Okay, so if you really want to use the potential method, which is what I usually use, so it is like if we have a L, if we have a C like this. Okay, maybe I just leave it next time on Thursday. So let's end it now.